as mentioned by Jeff, my title is Ground Improvement Approach for Airport Project with very high geotechnical variability. So I was the advisor for the design consultant, and this is prepared by us, myself, and the design consultant teams, Mr. David Sukamta, Ms. Helen Francisca, Ms. Putri Gandina, Ms. Evelyn, and as well as Mr. Dolok Panjaitan. So the airport project itself is part of the Indonesia push for infrastructure development. So President Joko Widodo put a priority on infrastructure development, and he set some so-called national strategic projects. And this project is part of that national projects. And the government also pushes for a public-private partnership scheme for this project. So this project is actually the first public-private partnership project for airport project in Indonesia. So in reality that we need to consider the perspective of the private sector as well as the government. So we have to deal with the both perspectives when we design this airport project. So the project initiator envisioned that the airport should be able to accommodate the Boeing's 777-300ER, which is one of the heaviest aircraft in the world at this point, commercial aircraft at this point, so that we need some quite a long runway for this project. So it is the runway will be 3.3 kilometers long and 45 meters wide. So this is the background, short background of the project. The project itself is located in Kediri. It is in East Java. So it is about 700 kilometers from Jakarta and about 120, 130 kilometers southwest of Surabaya, the second largest city in Indonesia. So you can see that Kediri is located somewhat on the southern part of Java Island. And that is actually important in terms of the seismic conditions of the location. And if we look at the a more detailed map of this project, you could see that the locations in a yellow circle is located northwest of city of Kediri, and it is located on the foot of Mount Liman. Gunung Liman means Mount Liman, and you could imagine that what kind of materials available in that area due to the volcano. So the Mount Liman was stratovolcano mount, and it is considered dormant. Hopefully, nothing will happen during the lifetime of the project. But it is now considered dormant, so so the investor is quite confident that it could do the airport development in that area. So that's the background that, wow, when we saw this project for the first time, wow, this is going to be a very challenging project in terms of the geotechnical variability of the materials. So this is the outline of my presentation. So I'm going to talk about the more detail about the challenges and how we did the soil investigations, and we needed some strategy for that. And I'm going to talk about two different things. First, about the runway and the ground improvement required for the runway, as well as the trial test conducted for that runway. And I'm going to talk also about the mechanically stabilized earth walls. And there is a special case that the MSE wall is interacting with the one of the large box culvert. So it's a very interesting part of this project that we need to consider the interaction between two geotechnical structures, and we need to do some very detailed calculations to make sure that these two structures will perform as expected. So again, as I mentioned to you, the location of of this airport is in Kediri, and if you could see the red arrow, yeah, this is the locations of the project. Yeah, as it is in the southern part of Java Island, and it is not too far, you know, from the so-called megatrust of Java Sumatra megatrust. So it is the major seismic source for Java Island, especially in the southern part. So we have to design our airport accordingly to anticipate, yeah, an earthquake, yeah, from this megatrust seismic source. It is an active seismic source in Indonesia, so it is a matter of time that we will have a major earthquake in that part from the megatrust of Java Sumatra megatrust. And we also have in Indonesia a more detailed seismic source map. And if we look at this part, the red arrow again is the locations of the project. We fortunately have no direct or near fault conditions. The nearest fault is about probably 50, 60 kilometers to the north. So we don't have any direct interactions with active faults in the region. But again, overall, we need to consider all these seismic sources when we do the design. And if we look at the seismic peak ground acceleration map, our standard code, geotechnical codes requires that we design the geotechnical structures to a PGA of for 10% of probability of exceedance in 50 years, so about 475-year return period. And so we adopted this value. And if we look at the area, yeah, it is the PGA at the bedrock level is about between 0.2 to 0.25 G. It is quite large PGA for geotechnical structures, and that actually affect our design. So this is the seismic background of the locations that we need to consider very carefully, and to make sure that the project will survive real major earthquakes in the future. And as it is located on the foot of Mount Liman, we also check the geological map, and there is a susceptibility to landslide map, yeah, developed by the Agency for Geology. And if we look at this map, we found that fortunately it is not within the high susceptibility to landslide. It is in between the very low zone and the low zone. So hopefully that based on the experience of Agency for Geology, we will not have any major landslide issues in the future. So then we look at the topographical map very carefully, because if you could see this directly, that the topography is very complex. Yeah, because of if you could imagine, you know, on the foot of a mountain, there will be some fingering of the flowing materials, And this is what we are having in this project, that a lot of fingerings that we need to take care of. And if you look at these values of the contour lines, you could see 100 to 125 or even 150 meter elevations within a very short distance. And this is really provided us with major challenges regarding how we could have a relatively flat infrastructure in this kind of terrain. So starting from the beginning, we paid a lot of attention of this terrain to make sure that we don't miss we don't miss any major issues regarding this terrain. And this is another big challenge that we need to take care of. And so to visualize this easier, this is the 3D projections of this contour map, and you could see how that contouring interacted with the planned airport. And you could see there is a major cut, and there will be some major fill for the airport. So this is the consequence of the locations that we have to deal with. Also, if you could see, there are two blue arrows. Those blue arrows represent major creeks of the geological systems. So these creeks need to be considered very carefully when we do the geotechnical work, so that these creeks will not give us some major water-related challenges in the future. So the Agency for River Management told us exactly what to do with this, and we cannot argue with them because that's their authority. So we had to follow their directions to make sure that these creeks are manageable in the future. Although we are gonna put a major infrastructure in this area. So based on that, we created this cut and fill planning. And you could see that along the runway, from the left to the right, it is basically from south to north. Along the runway, we will have a series of cut and fill areas. And from the south, we have a fill area and some cut area. The blue ones are the fill areas. The brown ones are the cut areas. So you could see it is intermittent zones of cut and fill materials. So it is something that we have to do a very careful assessment of each zone to make sure that this will not create some problem in the future. So this is the depth of the cuts, and you could see that in some area the cut depth could go up to about 20 meters. So you could imagine that we actually cut a hill to make sure that we could have a relatively flat runways. And although in some areas in the northern the western part, the top part of this figure, we could go up about 15 meters along the western boundary. But those are for the surfaces area. So, but today's talk will focus on the runway only. So again, you could see that we will have some major cut area, and we also did some fill height analysis, and you could see again the area are distributed, yeah, along the runway. And in the southern part, the fill area is not that high. Yeah, well, it's relatively high, about like 8 to 10 meters high. But in the somewhere in the northern part, where we could have up to about 30 meters fill area. Again, this is a major challenge yeah, for us, because of we have to deal with that due to the terrain of this area. And so we again need to do a very careful assessment of the effect of the terrain on the geotechnical requirements. So again, we could have a fill area up to about 30 meters high. And if we look at the material balance, yeah, so we had to deal with about almost 13 million meter cubes of cut materials, and we have to do about 11 million meter cube fill materials. So we can say that we have no imported geomaterials. Yeah, although there is a surplus of the cut materials, but not all cut materials can be used as fill materials due to the fill materials requirements. We don't want to put just any cut materials to the system, so we have to do a very careful selections of the cut. So it was a major issue when in the beginning, because we have to set some very strict material requirements that could be easily implemented in the field, because we have to deal with a large amount of cut materials, and we have to do a very careful selection of the fill materials. So it was a major discussions, yeah, how to do material selections easily performed in the field. So this is the issues that we have to deal with. And when we look at when we started doing this project, we got a set of soil investigation results, and it was initially done in 2017, and the reports include about more than 100 boreholes and SPTs, some piezometers, as well as some seismic downhole surveys. And when we plot the results, unfortunately, it was that the previous soil investigation is not lined up well with the latest airport planning. You could see that the zone of the soil investigations is in this direction, but the latest planning of the runway is a different direction. So again, we can see that the soil investigation results don't match with the latest planning of the airport. But anyway, we can get ideas about the geotechnical conditions, and this is one of the early plots of the geotechnical conditions, and you could see that again the contour, the terrain of the area that go up and down, and there are some gullies, some hills that we have to take care of. And if we look at the materials, the profiles, it's very complicated, and it is common actually in mountainous area in Indonesia that we have this kind of soil profile or geotechnical profile. And if you look at this, you could see number 1 in circle is basically clay silt materials. So you could see the major, the predominant geomaterials are clay silt materials. And the number 2 in circle are for sands, while the number 3 in circles are rocks. So again, the predominant materials are clay silt, and you could see some sands as well as some rocks. And the second number is the SPT values. And the second number one is for the very soft or very loose materials. So we could, number two is about the medium materials. So we could see that we do have some not really good clay materials, because we will need to have relatively high fill materials. So this gives us some ideas what kind of project that we are dealing with. So we need to put some major geotechnical investigations to provide us with much detailed geotechnical conditions for this area. This is along the runway based on the 2017 data. And this is one of the cross geotechnical profile crossing the runway. This is for the one of the major box culvert. And you could see again, there is a gully that we observe in the field. And again, the materials are very significantly in terms of the types of materials, as well as the stiffness, yeah, or the density of the materials. So again, we have a very high variability of geomaterials for this project. The red line on top of the contour is the proposed final elevation. So we could see that we need some major fill in this gully. This is another cross section, yeah, along the runway, across the runway, and again the red lines is the proposed runway elevations, and we could see that we will need some major fill materials. And you could see some gullies, and you could see that the gully was filled with materials. And this is quite common in this kind of area that we need to deal with. Although we also have some rock outcrops. So we have very high geotechnical variability that we need to deal with when we consider the geotechnical design for this project. So when we started doing this project, we proposed a lot of additional geotechnical data. So about 120 boreholes were conducted in 2020, and about 200 CPTUs and CPDs, as well as some piezometers. So we want to do more geotechnical profiling to make sure that we don't miss something major in our design. So when we proposed the 2020 soil investigations, we really carefully examine the proposed cut and fill planning, and the most of the additional geotechnical investigations were conducted in the high fill area, because that would be the most critical area in this this runway system. And as I mentioned to you, we do have also a major box culvert to divert the creek. So again, the box culvert will be underneath the high fill area. So we want to make sure that the box culvert would perform as designed. So we don't want to have again major uncertainties in the box culvert design. So we did a lot of soil investigations on this area. So again, this soil investigation, the 2020 soil investigation, was really designed to accommodate the high variability of the geotechnical geomaterials observed in the 2017 soil investigation results. And we have combined those with the proposed airport configurations. So again, when we face this kind of challenges, we need to put our focus on where it is really necessary. So again, this is to address the challenges that we talked about earlier. So again, this is, you could see, I should have clicked this before, and you could see that the locations of the soil investigations are correlated to the high field area. So based on the additional data, we do some seismic site class analysis, and we have a very high variability of the geomaterials. But then at the end, we decided that we don't want to be too optimistic about the seismic class because of this geotechnical variability. So we decided to stick with the site class S, E or D, if you are familiar with the ASCE or NIHR classifications, site class classifications, and we in Indonesia we adopted those classifications. So basically, we just used class E and D for the seismic design. Although we know that in some area there are some rock outcrops that could be much better conditions, but again, due to the variability, we don't want to be too optimistic about the performance of the system. So about the runway and ground improvement, so the major design criteria are the settlement, including the maximum differential settlement, as well as the post-construction settlement. The maximum, we adopted the criteria defined by ICAO as well as by the Ministry of Transportation of Indonesia. So basically, the maximum differential settlement is 30 mm in 45 meters, or about 1 to 1500 ratio, while the maximum post-construction settlement in 1 year is 20 mm, while in 10 years should be less than 100 mm. As we have predominantly clay sheet material, this is something that we need to consider very carefully, because we don't want our runways to have excessive settlement. And given that the fill materials vary significantly, and we also have some cut area. We really want to make sure that the settlement will not vary significantly along the runway. That would create the long-term problems for us, so that these settlement issues are major issues that we need to consider. So again, we can come back to this cut and fill zoning. And the lower figure is the cross sections along the runway. You could see that in zone D, we will have a major fill area, while in the southern part, in the left side, we have like a 8 to 10 meters fill area. So again, we have a significant terrain problem in this project. So we then, again, as I mentioned to you, this is a public-private partnership project. So we have to deal with the private sector as well as the government, and both sides highlight that the cost should be very cost-effective. So we really did major studies regarding how we could make sure that the performance of the runway is within the design criteria, but the cost will be very cost effective. So we came up with the scheme that, well, of course, we have to deal with the settlement issue along the runway. Again, we have a very varied geotechnical conditions for the runway. So we need to do a very detailed analysis, to make sure that the predicted settlement will be was within the design criteria set by the government as well as by IKO. So we think that we need to optimize the geotechnical conditions for the runway, but we also have some slope issues because again we have a very high field, about up to 30 meters high. So we will have a slope stability issue, and in some part we have to introduce MSEW, and we have to use MSE wall because there is a social problem in that area because the people there don't want their land to be bought by the investor. So that's why we need to introduce MSE wall to address that problem as well. So we have a variety of geotechnical structures that we need to consider. So this is again basically our geotechnical ground improvement scheme. But then we have to face the common perception. Well, you are building something in the mountainous area. Why you need ground improvement? So it took some time to convince that we need some ground improvement is needed for this project to make sure that the design criteria to be fulfilled. So again, from the ministry told us, do you really need that ground improvement? So again, we have to argue back and forth to make sure to ensure that they understand why we need to do some ground improvement, although it is located in a mountainous area. So then we really have to optimize the ground improvement area zones. So we've come up with this optimized zones, so-called segment 1, 2, 3, up to 7. Those are the areas that will really need some ground improvement. So the parties involved really scrutinized where we really need the ground improvement. So that's why we came up with this scheme. Although if you notice that the darker blue fill area is not part of the ground improvement. I will tell you why, the reason why we don't need. Well, we then skip the ground improvement in that area. So we did very detailed analysis about for each panel to make sure that everything is within the design criteria. So we came up with this. I'm sorry, it's still in Bahasa Indonesia. We could make, based on our earlier data, we could make a settlement profile of the runway. And we found that we're still okay in terms of the maximum differential settlements. But we cannot, we still have problems with the post-construction settlement. So that's the reason why we introduced the ground improvement schemes for this runway, again, due to the maximum post-construction settlement that we need to take care of to make sure that the performance of the area of the runway will be okay. And if you look at this figure, again, in the darker blue area, you could see that the rock is actually quite shallow and not that deep, not shallow, but not that deep. So we don't have a rather thick original materials to deal with. That's why we can just use the construction period to make sure that we will have no major settlement issues in the long run. But in the middle part of this right area, we do have a rather thick clay silt materials. It's up to about 20 meters deep. So this is where we need to consider the settlement problems very carefully. So that's why that's the reason why the ground improvement schemes is focused on this area, because we have a combination of relatively thick fill, and relatively thick and natural clay set material. So this is where we need to consider our ground improvement. Again, this is in the context that we have to address the construction costs very carefully as well. And then we introduce the ground improvement again in some part, not all of part of the runway. So we've came up with the reasonable number that we could fulfill the design criteria of the maximum post-construction settlement. So this is basically the schemes of ground improvements. We introduce two different ground improvement techniques. First is the typical stone columns, the dry bottom fit stone columns, and the other one is the deep dynamic compactions. The DTC method is actually quite new in Indonesia. So the contractor proposed this to the owner, and then they accepted that they could use this DDC. So we actually have two different methods to improve the soil. So that is the one of the additional requirement from the owner. Then we did some trial tests to make sure that everything will be within our target range of geomaterials. So this is for the runway. So this is some pictures of the, this is the prior to the construction. You could see that the contour of the area. Then this is a picture during constructions, and this is from east to west. You could see how high the fill materials are, and this is at the outlet of the one of the major box culverts. This is from the other side, and you could see also the cut, the height of the cut, and the height of the fill materials for the runway as well. So this is the latest picture that we get from the field, and you could see how this construction progress is still ongoing right now. And it is, again, if you look at this, the size of the heavy equipment, they were like toys, because the size of the embankment, the fill for the runway itself. And we also get some initial results for the settlement. And what I'm trying to say here is that while it is while our proposition that we need to do some ground improvement is proven to be true. We see that even after the embankment fill height is relatively constant, we still have we can see still some settlement of the embankment of the fill. This really suggested us that it is still clay and silt materials, that so it would we would have some settlements with time. So we actually glad that we did some ground improvement to make sure that the long-term settlement is within the design criteria. Because although it is in a mountainous area, we still need to be very careful about the long-term settlement. to make sure that our geotechnical structure will perform accordingly. So we, to make sure that the ground improvement techniques are proper, we did some trial tests. And for the stone columns, this is just a typical stone columns ground improvement. And as I mentioned to you, we have to use cut materials. And so we, as the materials itself vary from natural sands up to rock pieces that we have to crush them. So we have to use a different material. So we did some very thorough grading requirements to make sure that all the although the parallel materials vary significantly, we still have good materials for the stone columns. So they often in the trial phase, after they installed one of the stone columns, and they did some borings to make sure that they will get good materials, and you could see that the SPD values varied, and they are in a good range of density of the materials. And they did also some test bits to make sure that the diameter of the stone column is within the acceptable limit. And they did some static load tests as well, and to make sure that the assumed modulus for our analysis is achieved. The minimum modulus is achieved in the field. This is one of the static load tests conducted. And what I want to say is that when they did back analysis, we could see that soil elastic modulus varied significantly. Although again, the source could be the materials of the stone column itself, because again, the parent materials vary, and we still also have that natural materials variability. So this could be due to both variations, and so that's why we get this very high variability of soil modulus obtained from the back analysis of the load test. So again, when we do this kind of project, we have to be very careful not to be too optimistic, because again, we need to consider the high degree variability of the natural materials as well as the fill materials used, because again, the parent materials have varied as well. So this is for us, it's a good lesson that we were glad that we were not too optimistic, honestly. And so this proved to be true, that we have to be very careful to select the modulus because of this high degree of variability of geomaterials. And we also did some trial tests for the DDC. If you are not familiar with DDC, basically it is like a torpedo-like ram material, a ram hammer. So it is just dropped like a typical dynamic compaction. Yeah, but then the shape of the rammer is like a bullet. So again, we have to use the different types of materials. So we also use different sources of materials. One is based on surface miner equipment. The other one is just based on the rock excavation. So we use a variety of materials to make sure that we are in good understanding about the behavior of these ground improvement techniques. So they did some indicative size, and we could see that the variability of this product, trial, quite significant. We could see that the end product quite varied, not really significantly, but quite varied. So we need to consider that this as well in our evaluation. And they did also some test bits to make sure that the diameter, indicative diameter is also true. So they did some test beds as well. So they did some static load test for this DDC, and this is two tests, yeah, very close to each other. And again, we have variability in the parent matrix of the field materials, as well as the original ground conditions. So yeah, we get this very well, rather different results, although they are very close to each other. And again, the variability of the original conditions would translate into the performance of the ground improvement, this kind of ground improvement as well. They did 7 tests, and you could see that in different parts, and you could see that the variability of the load test results. Again, if we have this kind of project in the future, we need to do a careful assessment of what kind of performance that we could expect in the field. Again, we need to consider the natural variability of the geomaterials, as well as the natural variability of the field materials, the compacted materials, due to the variability of the parent materials. And they did also some borings and SPTs to check whether the DDC would affect the soil in between the DDCs. And what we found is that probably due to the initial conditions is not that bad. The increase in SPD values is not that significant due to the compaction of this DDC. So basically, when we design, then we should not expect that the soil in between for this kind of materials, the soil in between the ground improvement would be affected significantly by the ground improvement. So this is also something that we confirm in the field. And for the MSEW, the most controlling design criteria is the seismic one. So this is very important for us, because then we will have a very high MSE wall up to about 26 meters. And we have to make sure that as I mentioned to you, it's a matter of time we will have a major earthquake in the southern part of Java. So we have to make sure that our MSE wall would perform well in any major earthquake event. So we really pay attention to this zone because of the conditions, and you could see there is a creek. This is one of the major box culvert in the area, and you could see that there is why the reason that we introduced MSE wall is that it is very close to the land boundary, and so we cannot extend that to the natural slope option. And again, we have a terrain issue. You could see that the red lines are the contour. You could see that along the MSE wall, we are going to have a very steep change in terrain, as well as the materials. If you look at the middle one, we could have a relatively shallow bedrock, but next to that, we're going to have some relatively different materials. So again, not only the terrain, we need to consider the high variability of the natural materials in this area. So after very, very long discussions, we studied many different options of ground improvements to this MSE wall. We finally had to use some combinations of board piles, because the ground improvement itself cannot withstand with the seismic force. So, but to optimize the cost, we then combine the board piles with the some rigid inclusions to make sure that overall we are still in a cost-effective zone of the in terms of the cost. So that's this one of the picture during construction that you could see it's a massive foundations for the MSE wall. So, but then we still have a problem because there is an interaction between the MSE wall and one of the box culverts. And you could see the box culvert is oblique relative to the MSE wall. We tried to persuade whether we could just have a orthogonal box culvert to the MSE wall, but then it got rejected. So we had to deal with this oblique direction. The problem is that when we have an oblique kind of arrangement, we're going to have a twisting behavior of the box culvert, and that is something that we don't want to happen actually. So that's why we need to put some effort to make sure that there will be no twisting of the box culvert and due to the non-orthogonal arrangement. And unfortunately, we also have a very relatively soft materials in that zone. So again, we need to do some combinations of board piles and rigid inclusions in this area to make sure that the MSE wall is stable, and in order to ensure that the box culvert is not twisted. So it is a major challenges for us to analyze this kind of interactions, and we had to do some full 3D analysis to make sure that everything is covered. We don't want to have major issues during lifetime of this project. And so this is the picture of this area. And you could see this is the outlet of the box culvert, major box culvert, and you could see again the heavy equipment look like toys in this area, and you could see how the oblique direction of the box culvert relative to the MSE wall. I think that concludes my presentations. Again, hopefully that this presentation could give you some lessons that we have learned from this project. And again, I would like to thank Jeff for inviting me for this event. Thank you.